I'm Zoheir Sabeur from Bournemouth University, and as Samantha mentioned, I was in Southampton University 3 years ago before I moved to Bournemouth. Today, I would like to talk about an applied research program that I've been pursuing for many years and continued doing it even when I joined Bournemouth. So in terms of the content, I'd like to sort of emphasize about the increases of malicious attacks in urban spaces nowadays, and the IoT and big data and deployment of big data technologies that are available to us nowadays, and where does data science and AI sit in for trying to overcome this challenging problem, malicious attacks in urban spaces. So in terms of AI for behavior detection, so in context of cyber behavior detection and also physical behavior detection, and all in this is sort of wrapped in a project that is ongoing. In fact, it's a continuation of other legacy projects that I conducted in the past. And this one is the most recent, called S4 Cities. And it's with regard to AI for safer urban spaces. So I'll talk about the flagship project more or less, and the development of digital twins for safer and secure urban spaces that we're developing in this program. And I will project some future work that is ongoing. I should emphasize also that the project started, the S4 City started in 2020, right at the start of the pandemic. So it was quite challenging to work with a consortium of 27 partners remotely. And there will be Q&As, yeah. So over the last few years, various malicious and terrorist attacks occurred in European cities and others around the world. These caused fatalities and disrupted peace and security for citizens greatly. But they also crippled the operational function of some cities altogether, with obviously substantial economic losses. So cyber attacks and physical attacks of malicious nature can disrupt the function of a city, and it can cause, in addition to potential fatalities, a lot of economic loss. So, but what is strange is that it happened in the last 10 years, in addition to these known typical type of attacks that we encountered over the past, using, say, firearms and heavy weapons and so on. There has been an increase of attacks using low-cost methods like cars, lorries, motorbikes, knives, swords, etc. An example is this attack that happened in a museum in Brussels in 2014. And then another one, like a car attacks in Nice, in France, on Bastille Day in 2016. And also a lorry attack at a Christmas market in Berlin in 2016. And there has been more, like the one that happened in Liverpool recently in 2021. So these are very serious matters that we need to sort out in terms of protecting cities. On top of the increasing physical attacks, the cyberspace is not being spared either. So various cyber attacks occurred during the last decade, including DDoS attacks and ransomwares and more types of cyber attacks all over Europe and the rest of the world. For example, the one that I wanted to sort of exemplify here, ransomware virus scripting a request for cash payment attacked the German rail transport system altogether on May the 13th, 2017. This one started specifically on the electronic travel announcement board system at Berlin's train stations. Then the virus propagated rapidly across Europe communication networks, and including the UK, the UK NHS communication services for 48 hours. I mean, can you imagine this to happen during the pandemic? I mean, this is crazy. But I wanted to give this context because the vulnerability of cities has never been so high, particularly when both cyber and physical attacks occur in a synchronized way. We haven't got many of those, but they are on the increase. So the whole idea is that IoT rapidly generated big data sources over the last 20 years. And we created this cyberspace, there's communication spaces through communication network in cities. Basically, cities have been IoT'd, if I can say. And we created this big data sources of heterogeneous nature, certainly. Uh, it is made of structured, semi-structured, non-structured data with all that sort of challenging high in V's, including velocity and volume, variety, veracity, and so on. There isn't a particular sort of official definition of these V's, but the major ones are really volume, velocity, and variety. And when it comes to veracity and so on, you can argue about that. And more than 85% of valuable information is unstructured and exists in the form of natural language, text, reports, emails, and so on, memos, and so on. So this data exists around cities. All the mainstream media and social networking channels are dynamic communication that happen in the city, and all these could be exposed to attacks. That's in the cyber world. The physical world is there. It's been attacked before. So city connected. All modern major cities in the world are high IoT connected. So it is important to give that sort of context for the audience here. So in this sense, there is a need for critical management of big data in context of urban spaces operations, as it relies on, it should rely on, well, it is relying now onto IT infrastructure with core application designed to support decision-making groups. So city authorities need to have this infrastructure available, reliable, credible. All of that is important. And ideally, the cloud services for on-demand and secure data access should be made available. I put an analytics in brackets. This is not a finished business for all, this is important types of technology availability and reliability to counter the types of attacks that could happen. So a need for ad hoc connectivity and configurations, if you like, configurability is important. And these are mostly available, more or less, I would say, and with reliability and good connectivity. In 2021, for instance, we went a long way from the various commercial commodities nowadays. So all the big players, like IBM, Google, Amazon, and so on, are giving this kind of availability and as basically a commodity. So you can see all this landscape. This is 2016, but I haven't got an updated version of that. All these infrastructures are available in most modern cities, available not just to authorities, but also citizens. However, a strategic data processing framework needs to be put in place on data analytics. The data analytics business for knowledge extraction and discovery for citizens. Citizens, including people who are actually doing governance of cities and regulations in cities and so on. The data analytics for knowledge extraction is not yet available to everybody. So core analytical services are yet to be developed. The management control of data under comprehensive policies, governance guidelines, and their ethics and legal matters with ISO standards are still sort of yet to, particularly for the monitoring system that we put in place. So this will only allow the capture and extractions of data, of big data from trusted sources, of course, and make a meaning out of that. So the performance of data science and AI for delivery to the right extracted knowledge actually lead to this, what I want to call advanced situation awareness. And this needs to be delivered to the right people and at the right time for critical decision support. This all relate to when we are attacked in a city, either in the cyber world or the physical world or both. But again, the question is, are cities deployed with advanced situation awareness systems? And that's the problem. So where the data science and AI sit in? This is a question I needed to ask before I go to my project. So the whole business of data pre-processing is an entire piece of work in its own right. You know, the management of data quality, the adoption of metadata standards, the understanding of provenance and trust from the data, the semantic gaps that occur in the data that is developed, that is generated by IoT components, the conflicts that result from out of that, and you have to reconcile that. The gaps that exist in data, these are all types of, if you like, pre-processing that needs to be put in place and available to everybody to actually even start thinking about doing some analytics and doing some knowledge extraction. I mean, the asynchronicities between data and their multi-modalities nature of that are immense. So at this low level of data, low level of data science, if I may call, the data pre-processing needs to be achieved and overcome. Then you go into the post-processing of the data and you can harmonize, so you can start beginning or start to begin creating new knowledge. You aggregate data, you install a trust matrix in place, you can differentiate between data sources and their credibilities and so on. Then you move to a high level, which I call mid-level 2, on being able to mine and explore data, because this is where you begin start doing your research work, really, you know, how you cluster data, tools for that, background extraction, foreground detection or recognition, and so on. All of this is important before you head to learning. The achievement of high performing learning with correct classification rates and so on above you know, targets that for instance the customer or the client who funds you to develop the tools to go beyond 90% and establishment of good confidence levels. These are all the challenges. But after that, you want to go further into modeling what you're discovering and what you're seeing as patterns, and model the uncertainties that you obtain from your models and how to propagate them in time and space. All these are important activities in data science and AI. So with that, you will be able to forecast with control uncertainties. But above all, you need to develop the context into which you use these tools. The context needs to be achieved through knowledge modeling. For instance, you know, you could have, because we're heading to intelligent decision support system, for instance, and the knowledge modeling at this high level needs to be put in place. You cannot predict a particular anomaly in the data and say, this is a problem. You need to put it into context. An anomaly in a particular space, urban space that is, discovered through data, say communication network data, could mean just something benign happening. In another space, it could be anomalous. So the context is important and you need to reason upon it. So all this kind of hierarchy in the data science and AI activities is important to be aware of and also apply, particularly in a multidisciplinary project like we're in. So I talked about low-level data pre-processing, the post-processing, the data mining, the machine learning, the modeling and reasoning. And these covered areas is where probably most people talk about and consider as AI. So AI could sit there, but it is important to not to talk about, not to say that I have a tool based on AI without going to higher level in terms of modeling and reasoning. So that's the thing. Modeling and reasoning is not, if you like, used by the majority of our academic communities. So it is important that we do that as well. So let's go to the cyber behavior detection now. I wanted to, and I insisted to introduce you with sort of the context of where we are with data science and AI in terms of dealing with urban spaces, safety and security. So the cyber behavior detection, the rise of machine-to-machine connection is even more significant, growing from 6.1 billion in 2008 to 14.7 billion by 2023, which is not very far, 2 years' time. So these communications are increasing, and I believe that this data, this data needs to be reviewed. This statement I probably made it before the pandemic. So the pandemic is giving us probably more responsibility to consider this and be aware that the amount of connections have ever increased in the last 2 years, really, and our vulnerability to attacks is ever so big. So this is due to the growing use of IoT devices the last 2 years, I suppose. So with this influx connection, it is inevitable that with that, internet traffic will grow and becomes increasingly challenging, and the malicious connections will increase in urban cyber communication spaces specifically. So we initially used the exemplar network traffic communication dataset for the automated detection of unusuals in cyber environment in the S for All Cities project. These included these type of datasets, which are open datasets, and the structure in terms of usualness and unusualness is of this sort across the 3 datasets. And we use them, we select them with their good range and similarities in terms of their diversity in terms of anomalies and normal conditions. This was the first test. And we implemented 5 classifiers with their performance analyzed. So these were the naive Bayes, logistic regression tree. This was the first test in the initial period of the project. We are entering the 2nd year of the project, so this is last year's work. So in terms of accuracies and performances, the various data sets up against these classifiers is as follows. You can see that many of them reach high performances, although some actually do not do well. So this is across the 3 data, and just referring a note on the MCC as it was calculated. So with this data, I cannot go through all these numbers, but you can see or feel where things are doing better than others. So overall, these classifiers appear suitable models for an IDS system, for instance, to monitor communication network behavior in urban spaces. But across all the 3 data sets, DNB, the naive Bayes classifiers didn't perform well. The LR and RF models performed averagely well, but the other 2, DT and GPT, show that they are stronger and consistent across the board in terms of performance. But overall, GPT is recommended in this study as it consistently has the highest recall and MCC values. In terms of what we have used, because we wanted to scale, we used Apache Spark cluster to do the Spark jobs that were managed by Yon for scalability, and indeed it scales. It is important to do that because the aim is to deal with a larger data set, if you like, representing realistically various regions of a particular urban environment. To when you finish all these kind of calculations and the understanding of the performance of the machine learning algorithm or the classifiers, it is important to see if we distribute them across a cluster, given cluster. We use 2 clusters initially with my research students, and the scalability is good. So it is important to go further into the scalability work, and this is ongoing for the second year of the project, which has started a couple of months ago. So in terms of training time or running time of Hadoop clusters, as I said, you can see that we have good performances, well, good running times, if I may call it. It gives some interesting abilities to do the runs in good timing. Recall that we want to, if you like, achieve the critical capability of the system, and by the end of the As for All Cities project, we want to scale to the level that the user, particularly cities, we have 3 cities in this project who are the end users, will be satisfied by the response of these systems. So in terms of physical behavior detection, the question is, can we predict and prevent? Now we're talking about the physical attacks. Can we predict and prevent intentional malicious behavior in an urban space? Can we detect unusual seed behavior and prevent its propagation in crowds? That's important. We are very much sort of focused on the beginning of a particular malicious behavior or intentional malicious behavior within a crowd, or within a reasonably good number of people in a smart space, or smart space meaning that it's monitored. We have all the IoTs to measure what's going on in it, yeah, including cameras and sensors and so on. So these are the questions. The seed behavior is important because we are interested in its propagation. Its propagation in the crowd. And of course, can we scale the above detections of human behavior and understand in a large crowd system, a large network of monitoring cameras, for instance. So that we haven't done the scalability part yet, but we will do it. An example could be like, for instance, a stadium with 70 cameras. I visited a stadium in Spain where they had 70 monitoring cameras, and the capacity of the stadium is around 35,000 people. The flagship project that I talked about, I want to mention them. One is called the Evacuate project, evacuation of crowds during crisis. And we did with that crowd behavior understanding with computer vision features extractions, and deployed some statistical mechanics principles to actually aid ourselves to understand behavior. So you can extract feature on a scene, but to understand the scene, you add on some theories to actually guide you to make up your mind, particularly on, or the machine making its mind, if I say, whether the activities or the behavior of humans is malicious or not, or unusual, to be sort of politically correct, I would say. There is another project called ZoneSec, and this is about the detection of malicious activities in white zone. White zones are critical infrastructures like stadiums, airports, you know, tube stations, underground tube stations. We did all of that, and again, we worked on unusual behavior in these CIs, critical infrastructures, and we use multispectral observations like optical, thermal, and hyperspectral, as well as acoustic and radar in this project. Knowledge modeling is important. As I said earlier, the context ontology modeling to CI's operations were performed in ZoneSec actually. Basically for every site, for every urban space, if I may call it, with critical infrastructure, there is what we call a native knowledge that is understood by the practitioners, the security and operator practitioner of that urban space. So this is something that you need to grasp so that you develop the knowledge model and give added value to your detections and give it context, whether it is unusual or usual. And this one, I call it high-level data fusion and reasoning in order to issue critical alerts. When you discover that you are truly having an unusual behavior going on in the physical space. But these concepts also apply in the cyberspace, or both. I mentioned the word fusion because I'm using what we call the joint directive laboratories type of information fusion model. I'm not going to talk about it here because of the time, and it is important that I care about time because my slides are numerous. These are useful references for the audience to give you the context of the research work that we've done in evac and ZoneSec. The ongoing project that we have in Bournemouth is the S for All Cities. This is ongoing. It started right at the beginning of the pandemic, but this is still ongoing up to 2023. So it's about, again, the detection of unusual behavior in smart urban spaces. It builds its research from, as I said, on various projects. I even mentioned other projects like TRIDEC and InfraRisk, in addition to Evacuate and ZoneSec, important investigative research project. And it's all about understanding intentional behavior. The aim where we are sort of driving on is intentional behavior understanding using computer vision and fundamental statistical mechanics principles, but in context. And we would like to do that at micro level, so an individual level, at a mesoscale level, as a group of people within the crowd, and at a micro level or macro scale for the whole crowd, seen as a blob, behaving with a particular macro level. So in a way, we are looking at micro behavior understanding, meso behavior understanding, and macro behavior understanding. This is an open research activity we're doing with my team. And with that, we are developing a digital twin that actually captures the cyber and the physical behavior in a smart space. And the digital twin we're developing, this is ongoing, it's called MAIDS, which stands for Malicious Attacks Intelligent Detection System. And it specializes in the following: human physical behavior understanding smart space, cyber behavior understanding smart space communication network, and it does the high-level fusion of cyber physical behavior through modeling and reasoning for the critical issuing of alerts. So the modeling here is based on native knowledge for specific pilot cities that we are working with in the S4C project. This part, the higher fusion, is done by a partner in Greece at the moment. In terms of communication, the publishing of information that comes out of the MAIDS, that's communicating through Kafka technology with two additional external digital twins located in Europe, One of them is called the DEC IoT, and the other one is the ACMS. And collectively, MAIDS, DEC IoT, and ACMS will advance situation awareness using AI. They all use AI, by the way, and this will create this advancement of situation awareness in good context in a city space or city spaces, because you can, as I said, scale this technology to an entire city. But we are limited in this project by looking at specific spaces or smart space in various cities in Europe. So the DEC IoT stands for Distributed Edge Computing IoT Platform. That's done by our colleagues in Greece with with ICCS, and ACMS stands for Augmented Context Management System. These are two digital twins in addition to ours at the moment to actually connect. And I'm giving a recent publication we presented at the AHFE conference last July in New York, for that matter. So I'm giving you a kind of overall architecture or high-level architecture what MAIDS is vis-a-vis the SEMS and the DEC IoT. You can see various numbers there. These represent tasks in a program or sub-program that we do in the large S4 cities project. This one shows that there are many partners working on various tasks. The sixth one is done by colleagues in the Czech Republic, which refer to crowd simulation. These guys do crowd simulation in terms of using first principle based models of crowd. You got 6.2 with the IoT people with ICCS who are developing the platform based on the AJAX Foundry platform for the IoT, and other groups who are doing face and gesture recognition in Spain with us, company, the IT company, and we work on the unusual behavior detection module. 6.4, 6.5 is done by a company in Greece called Access, and ACMS. All of this is published or subscribed to. On the left-hand side, you subscribe observation about the real world, be it the physical, the cyber world, and then you move towards further intelligence on the edge at 6.2. And then when you get 6.1, you create more intelligence through extraction of knowledge about behavior or something going on in the smart space that you would like to publish, but it goes towards the knowledge modeling and reasoning module using a knowledge-based native database, if you like, or a native knowledge base. Only then it will publish it to the ACMS. The ACMS is equipped with intelligent augmented reality type of modules developed by a company in France. So the company is called DigiNext, and all this 27 partners across Europe will lead us to developing 3 digital twins and demonstrate them in 3 cities. One is Trikala in Greece, the other one is Bilbao in Spain, and another one in the other one is Pilsen in the Czech Republic. So as I explained, these are the type of activities that we're doing at our level in the S4 cities. What I mean by our level is at Bournemouth University. So if you look at the MAIDS, where it sits with respect, this is a kind of overall data flow. Another view of the communication of MAIDS with ACMS and DEC IoT. And on the left-hand side, you can see blocks of fusion. That's what I call they fall onto the JDL framework. It has various levels from the pre-processing, fusion and aggregation of data, to object assessment and situation assessment, to impact assessment, and pushing it to higher level fusion with context awareness, taken on board the native knowledge base. Only that done will communicate with the ACMS to raise the alert or say nothing's happening. The ACMS has access to all sorts of information for the user in this case. On the right hand side, when you see ID attacks and mass shooting, these represent some sort of scenarios that the end users would like us to achieve under the digital twins with the simulators and so on. Here you see the Apache Kafka clustering. Obviously, the means of messaging information in and out of this group. There you go. So in terms of some early activities that we did, multi-sensing of environmental parameters at various locations of smart space. We say, what's to do with physical behavior detection? Well, it does. That gives another context for thresholding on what is unusual or usual. Meteorological data actually matter, and they influence the behavior of crowds in the city. If weather is bad, you wouldn't expect people agitated in the city. It'd be mostly less frequented bad weather than a good weather. So all these are important to have access to. With that, we're using an RBF network technique or techniques using N sensors to achieve the fusion or spatial fusion of multi-sensor data. These are sort of the basic definitions of RBFs. But the good thing about this one is the prediction of meteorological data at meteorological parameters values at micro level can be done, and in areas where there is no sensing, you could have few sensors, but you can create some aspects of sensing the meteorological conditions in areas where there is no observation hardware going on. The other good thing that you can estimate these parameters, even if there is one or two sensors breaking down. So it adds value to the resilience of the MAIDS intelligence. So the MAIDS intelligence cannot wait. It keeps going. Obviously, the uncertainty will be higher if the uncertainty estimations on the predictions will be higher when a sensor breaks down. But overall, the uncertainties are controlled in this sense. The other good thing about it, it also gives us the other way around type of management. Basically, if a city authority would have a budget or have new funds to deploy sensor observations, this approach can actually optimize the calculations to actually identify where to put the sensors with lower uncertainties overall. Spatial uncertainties, that is. Going back to behavior detections of humans, we obviously we work closely with the cyber incident detection and understanding for reaching an overall view of the cyber physical world and understanding it, as I said, with high level fusion in context, using native knowledge to actually understand if the cyber and physical attacks are connected. So there is a possibility to investigate on that with such capabilities. Okay, the physical behavior detection, we're using multimodal observation methods, using vision and environmental context in this level. I put acoustics in gray form because that would be the next element. We want to hear the audio element of the smart space so that we can add a context understanding what's going on. But at the moment, we haven't installed that. Again, as I said, our aim is to develop the micro and meso and macro scale levels of behavior and understand them. At the moment, we are detecting and tracking individuals. Each individual is associated to an ID, of course. The technique also provides bounding box coordinates for all detected individuals. We have two methods. I mentioned the statistical mechanics based understanding of feature extracted in a scene. This one is done with our postdoc, Alessandro Bruno, who is now a lecturer at BU, and he worked on this activity separately. So he worked combination of deep sort and YOLO version 4 and 5 to track down human crowd movements over video sequences at micro scale. So his aim was the detection of individuals and re-identify them and generate their trajectories. I will come back to you in terms of why I'm after the trajectories. So if I go to these runs, you can see that we are able to generate these trajectories on an urban space. Same thing, I can run it here on space, open space or pedestrian space in the city. So the generated trajectories are extremely important for us to understand anomalous behavior. And it is important to generate those in a good scalable time when the data grows in volume and variety and so on. Just looking at time, yeah, same thing here. The upper right shows individual detections, and these are the trajectories that we have, and we extract these trajectories and look at the analytics of those. So the aim for these trajectories is to see how these trajectories connect with each other. And this is an ongoing activities by one of my research assistants, who is actually working as we speak on this particular subject or topic, is the classification of these trajectories at various scales. These are the micro and the meso and the macro. So you could have an overall trajectory of the blob crowd, or the understanding of a particular trajectory where we can merge together when they cluster and form a group, or actually demerge or separate and see that these guys are going different way and they have nothing to do with each other, or they had something to do with each other and now they are in different groups. So you can do also analysis mathematically after you detect all of these aspects of the trajectories. This is another piece of data where Alessandro Bruno developed using aesthetic or synthetic data to see if his activities for detection of and the generation of trajectories is valid. Same thing, this works, and I have time against me at the moment, but the system's capability on detecting individuals who are not standing, for instance, we found out with YOLO 4 not working properly, but YOLO 5 it works. So I want to go back to the statistical mechanics work, which I didn't have time to present it today because of time. We have developed this method using the concept what we call collectiveness. Actually, it's a measurement of the actual entropy. It's related to it. And we have inspired, obviously, molecular system thermodynamics. I recommend you to see the reference below, which we have published last year with my research colleague, Banafsheh Arbab-Zavar. And we can measure internal flows at various levels, the kinetic energies, and potentially the internal energies. The internal energies of crowd are the most challenging ones, and we're working on that, because you see, you could have a kind of a particular stationary activity with a measurable internal energy that could lead to a particular flow of crowd or individuals or groups. And this is something that we're working on. And variation of these kind of detections lead to various interpretation in time, particularly in the urban space, as we may reveal crowd behavior understanding within depth behavior details. For instance, crowd in panic states, group of individuals with the crowd unusually behaving, or one individual within the crowd unusually behaving. Also track the propagation and anticipate what would be the likelihood of this behavior specifically at various scales. And we can be on top of the, if you like, the management of the security and safety of the crowd. So these are about situations of great importance in safety and security practices in urban spaces. That's the one that we use with the statistical mechanics. Here we use an experimental work we did in a stadium in Spain, where we measured these flows and measured the kinetic energies, not the internal one, but this can tell us how group can separate and where they're going, potentially the likelihood where they're going. So the mixing of the other method done by my research assistant, as well as Alessandro, combined with my colleagues' work on statistical mechanics principles, can lead us to a more robust approach to actually understand the propagation of behavior in an urban space. Here we went to the stadium and we generated data with volunteers. The number of people used were around 80 people. In this case, there is less of them, a little bit less, but it was successful to actually prove the validity of the approach using collectiveness. The concept of collectiveness is very important to embed here. So in terms of future work, we will advance our research into the following: forecasting trajectories on human behavior and understand their multi-scale dynamics for future machine learning classifications, and scaling our performances in computer clusters. We have the Apache Spark and we have the GPU machines to do that. We will investigate more on the internal energy measurements. That's the highest challenge, because that even when we do that sort of with data, we still need to validate it and discover some intrinsic measurements or intrinsic parameters related to the to the physical space. Of course, we will deploy experiments in BU this year, 2022. Using our equipment for optical, thermal, and meteoroacoustic sensing. So I added the acoustic part here. So this is the aim to purchase that for from New Year onward. And we will capture the scenarios that the end users in the S4 Cities project asked us to consider on human behavior and validate our MAIDS twin AI modules in collaboration with the partners. We will experiment these in Trikala, as I said earlier, in Bilbao and Pilsen. These are all different scenarios of attacks of both cyber and physical, or combined. This research is being achieved due to the hard work of, I'm just finishing here. This is due to the incredible hard work of our research group on processes in behavior understanding. I thank them all, with no exception, including Dr. Denise Tinkaya, Dr. Alessandro Bruno, whom I mentioned earlier, Dr. Muntadar Salal, who works on the cyber behavior detection, Dr. Banafji Arbab Zafar, who has been working with me on the statistical mechanics principle combined with computer vision techniques, Dr. Marios Angelopoulos, who is on the IoT DEC IoT platform, communication with our Greek partners, and also Dr. Jamal Banauda, who just joined us for the publishing of our output from the digital twin, the MAIDS. Mr. Liam Kollick, who was my research assistant, who worked initially on the cyber data sets that I mentioned. He's working in industry now. And Mr. Marwan Farjani, who just joined us, who's working on deep learning in computer vision. So all of this, I should thank I should acknowledge that this research is partially funded by the S4 Cities grant by the EC under ID number 8883522. Thank you very much.